Hi everyone, my name is Asil and I will talk about our research paper called The Exchange of Knowledge Using Cloud Robotics, a joint work between University of Bremen and the University of Tokyo. So the Cambrian explosion took place almost 500 million years ago, which resulted in major diversifications of living organisms. Today we are almost at the same stage for the robots, which means that we have a lot of different embodiments specialized for different tasks, such as household tasks, undersea missions, rescue missions, like for a lot of different environments. On the other hand, these robots are still lacking of human level mastery because they don't have generalizable knowledge for their tasks. So especially for the household tasks, this brings two major limitations. One is adaptation. Like even a slightly changed environment or the hardware, the robot must be reprogrammed or retrained. And the second problem is the knowledge gap. If you move your personal robot to another home, and the washing machine that has a slightly different running process, that if the robot doesn't know about this, it will fail. So there are many different approaches to supply this kind of knowledge to the robots. The first major example is one that Google does, like putting many arms in a room, and these robots try to generate some random grasping data for their deep learning framework. On the other hand, these are really hardware and environment specific. So we cannot use this data for another robot in a different environment. So our goal is to establish open available semantically annotated collection of diverse datasets. Our vision behind that is that when the robot asks, hey, I want to open fridge A located in the environment B, can you suggest me a way to open this? And our knowledge system called openEASE can supply a sample trajectory to open this fridge, and hopefully the robot can execute that. So openEASE employs a common ontology that covers all relevant knowledge and concepts and their relations in the household domain. This brings two major advantages. Firstly, with this ontology, the robots can integrate different kinds of knowledge sources. Secondly, they have some kind of common language to talk about the things and the exchange of the knowledge between themselves. And secondly, when they are recording the sub-symbol data like the camera flow, joint information, and so forth, they can tag the sub-symbol data with the symbols from this common ontology to provide an abstraction to use later on for the queries. So in a way, we are seeing our knowledge service as a digital assistant for robots. It's like Amazon Alexa or Episodic for robots. And it's not just about the motions or the task, or I don't know. It's not about the motions or the actions, but we want to provide all the relevant task knowledge that robot might need. For example, in this figure, you can see that a high-level robot plan called fetch an object provided with a parameter called meatbox. And the planner first asks to the cloud, what is the type of the meatbox? that when it gets the answer pageable item from the cloud, it asks this time, where can I find this kind of items? So that instead of blindly looking everywhere, the robot might get a hint that it can find this kind of objects in the kitchen environment. So in this work, we establish an interface for openEASE. We call it openEASE machine interface. Using this WebSocket-based interface, the robots can upload new episodic memories or new knowledge to the cloud. They can use the existing ones from other robots, and they can use the remote inferring and reasoning mechanisms on the cloud. So in order to make this exchange of knowledge possible, what do we need? Firstly, as we talked before, we need episodic memories from task executions of other robots located in other environments. Secondly, robots' own control executives can be compatible with the interfacing with the cloud, so to speak, openEASE machine interface. And thirdly, we need semantic maps of the environment so that the cloud can have an idea which kind of environment the robot is operated in. And then we need the semantic descriptions of the robots to adapt the data between the different types of the robots. And lastly, we need some set of rules to adapt the data symbolically. So this is an example episodic memory recording that might highlight our data properties. Firstly, we are recording continuously our sensory data and joint level data, and camera flow, so-called this sub-symbolic information. And while these are recorded, we are tagging these at the important events. Like in this example, the robot finds plate on the tabletop at time point 2. Then it tags this time point 2 with a new event type detect, and it attaches object properties with this event and also attach the captured image and the image region. So now that we have some episodic memories and the robot asks, give me a trajectory for opening a fridge, the openEASE first tries to find a similar task which is executed by another robot or maybe in another environment. And when it finds it, it compares the source semantic map with the target semantic map. And using the semantic rules that is available in the ontology, it deduces some ways to adapt the data. In order to test our framework, we first executed some opening fridge examples with a PR2 located in Japan. And then once we have episodic memories from that robot, we use another robot, the fetch robot, which is a single arm robot, to connect to the cloud and change the trajectory from joint level data to and effector level so that it can execute the same trajectory. Also, we use the shared perception events between two robots to make the perception task easier for the fetch robot. And in the second use case, we use the same episodic memories that from PR2 in Japan to use that to use that information for another kitchen located in Germany. And in this environment, the PR2 has to open a different kind of fridge. And first, it needs to adapt the Gaussian model of the locating itself in front of the fridge so that it can reach the fridge door and opens it. Secondly, the adaptation of the opening trajectory needs to be done because the fridge has a different fridge in Germany has different physical properties, and in this time, the openEASE suggested that we need to widen the trajectory by 90 centimeters. And before using this adapted trajectory, PR2 in Germany uses the fast plan projection just in case to test samples for the reachability and collision problems. So here's a video from the experiments. Here our first of all, PR2 in Japan, you execute some opening tasks. Now the fetch robot tries to open the same fridge by adapting the trajectory for its own hardware. After that, we move our camera to Germany, and first the robot tries the original trajectory without changing anything. And as you can see from the video, the robot fails before opening the fridge completely. But when it uses the adapted trajectory as suggested by openEASE, it can successfully open the fridge door and manipulate inside the fridge. So as a conclusion, we offered a centered knowledge source and reasoning engine for household robots, and it's kind of a sharing mechanism for the robotic memories and the static knowledge located inside different robots. Other robots can use this information and can adapt the plan parameters and route models for their own use cases. So we believe that in the future, the way is not only going towards deep learning or machine learning approaches, but the hidden mechanism that make use of the symbolic level reasoning could be the best option. So, just after the launch, we have an interactive session at the port N.6. Please visit us if you are interested, and you can test out our queries plus data from openEASE web interface located in this website. Thank you.
Okay. Due to the time limit, probably we welcome one question only. And the question? This one doesn't work. Right? Just your one? Okay. So, yeah.
So how much can the trajectory be adapted? Like the two examples you showed, they're not that different.
Yes,
so what's the limits of adaptability?
So currently we can even adapt the trajectories between oven and fridge, So we couldn't test it because I had a limited time in the summer in Tokyo. But currently, with the available semantic rules, we can adapt like every opening container with a hinge joint can be adapted and reused. And we are right now testing like between the fridge, which is like this, and between oven, which is like this. And I think our semantic rules covers almost every physical properties of the doors with the hinge joint.
Okay, thank you.
Yeah.
Okay, thank you very much. So let's